Ladies and gentlemen, welcome to video number 27 in a series of 30 video lectures that are companions to the book The Fivefold Sun, which was filed at the Bibliothèque Nationale de France in late 2017. We are today, December the 12th, in the year 2018, about a year later. Today we deal with solar surface cells at the photospheric surface of the Sun. In the previous video was discussed what the characteristic sizes of these cells are, and now we will see in this video whether a cascade of tiling cells after icosahedral symmetry can reconstruct this observed sequence of solar cell sizes. This is the content of section A in part 6, which contains the entire discussion on the cascade of solar cell sizes. And we start with the notion of spherical icosahedral tiling after a recap of the findings of the previous video. Characteristic cell sizes. In video 26, we saw that the accepted hierarchy of solar surface cell sizes was given, for instance, by Mackintosh in 1992, the author of the canonical Mackintosh classification of sunspot groups. And we saw that this hierarchy of cell sizes amounts to a scaling factor of approximately 4. Then we reviewed a meta-analysis performed in the Fivefold Sun project of the literature since Mackintosh 1992, more than 2 decades ago. And in this 2017 meta-analysis for cell sizes down to 1 megameter, we found that there is not much to reassess in the findings of the estimates of Mackintosh, except that we found already in the second part of this work, dealing with the 3D volume geometry of the solar ball, there is a apparent bimodal distribution of the size of the giant cells. The mean scaling factor after this update is closer to 4 and again approximates this integral value. We will now see on a 3D model of a spheroid like the solar ball how this typology of cell sizes looks like in observations, at least in the accepted canonical estimate of 1992. In this 3D model, akin to spherical surface like the photosphere of the Sun, are shown the characteristic sizes of the solar surface cells as given in Mackintosh 1992, except that for the largest scale, the giant magnetic cell, are given now in orange and yellow, the two bimodal values that are found in this work about the central value for this giant cell given in 1992 by Mackintosh. So you see the orange cell is the largest one, the high bimodal value. It has, if it was a circular diameter of about 500 megameters. And the yellow cell below in the lower hemisphere has a diameter, if it was circular, of 400 megameters. This was the original value given for giant cell size by Bumba in 1969. Then we have in green a cell which represents the sunspot group size according to Mackintosh 1992, with, if it was circular, a diameter of 150 megameter according to this author. And near the middle of the green sunspot group cell, we have the very well-known supergranulation size, with its typical size, according to Macintosh, of 30 megameters. Finally, we have a set of pins with pinheads, and the heads of the pins represent the size of a single granule. So we are through now with the entire set of accepted major solar cell scales at the photospheric surface as found from observations. Now that we saw how the observed approximate size scales of solar cells can be seen at the solar surface in a 3D model, now we will see how theoretical regular dissection of the solar sphere, its two-dimensional surface, can reconstruct approximately this observed hierarchy. We will obtain the sought model from fivefold spherical symmetry with a radial projection of the so-called basic icosahedron that we postulate in the Sun's interior, and then successive bisections of the spherical arc edge of this icosahedron in the case of the Sun at the photosphere. We shall now investigate this again on the same kind of 3D model. This is now the same 3D model of a sphere with the same color code, except that the cells, instead of being irregular, now are circular. The yellow and orange cells are the giant magnetic cells with their two modes in size. The yellow cells represent the so-called vertex cells in the icosahedral circle tiling that will now be introduced. We see protruding sticks which represent vertices of the icosahedron in the interior. The protruding sticks are along lines which come from the center of the Sun, pass through the center of one of the 12 outer balls suggested to form the icosahedral setup in the interior, and they arrive at the solar surface, where they here represent the center of a so-called vertex giant cell, the predicted diameter of which would be 400 megameter, which is exactly the initially estimated observational value by Bumba in 1969. Then the orange cells, you see there are 5 of them around a vertex cell. One of the 5 is missing, so as to show the tessellation, further tessellation or tiling for one face. And these orange cells, which are called in this icosahedral tiling face cells, have a predicted diameter of 500 million megameter, which is also in line with the values from observations in the bimodal distribution that is proposed in this work. You see from each of the vertices to a next vertex is a line which represents an edge of the icosahedron projected at the surface, i.e. an arc edge. And the tiling proceeds through a bisection of this arc edge. Bisection means that it is divided in two, and from the middle of the arc edge to the middle of the neighboring arc edge is drawn a dark line, which you can see on the center of the face that is left open. And the three so defined dark lines compose a central triangle at the center of a face of the icosahedron projected at the surface. In this central equilateral triangle can fit four tiling circles, which indeed tile correctly because they are tangential. And the size of this, these cells, which are here in green color, is suggested to coincide with the cell of the cell scale of sunspot groups in the classification of McIntosh 1992, for which he gave an estimated characteristic diameter of 150 megameter. The predicted diameter of the green cells obtained from this tiling is here 132 or 33 megameter for each of these four central green cells around the red pin, which represents the center of the face that is shown. However, if we try to tile in the same way the triangles that remain at the angles of the face near the vertices, we will end up having, instead of equilateral triangles, isosceles triangles, and there will be smaller, so that the weighted average diameter of the tiling cells for the entire face will only be 118 megameter. The size of the green cells that are shown here is relevant to compare with the actual observed estimated size of sunspot groups, because the red pin at the center of the face represents the latitude of 10.9 degrees versus the equator, where there is the peak density in sunspot groups. Now, below this red pin, you can see a dark blue cell, which is suggested to represent the supergranulation cell. It is obtained from further bisection of the shown triangles, which is, however, not given in this model because it is too small. The predicted size of these dark blue cells representing supergranulation is 20.5 megameter approximately, which is within error bars exactly the same as the observational characteristic separation of 29.3 megameters. So this is briefly, for short, the procedure of icosahedral circle tiling of the surface of the sphere that is proposed here in the Fivefold Sun project for the photosphere of the Sun. So this is what we get from the proposed procedure of icosahedral tiling of the solar sphere in 2 dimensions. We reproduce more or less the observed hierarchy of solar-sized cells. How do we go about this in theory? This is not a simple process, and we shall try to go through this theoretical partitioning process for the 2-dimensional surface in a few pages. We have a number of levels of bisection of the icosahedron's arc edge from n to 3 first. Here we obtain with n equals 1 32 cells, with n equals 2 122 cells overall, and with n equals 3 482 cells. We shall go through this first and then separately go through the further bisections with n equals 4 and more. The first scale level for n equals 1 yields the 32 cells that are equivalent more or less to the giant cells at the solar surface in observations. There are 20 so-called phase circles and 12 so-called vertex circles, as you saw. The sizes of these tiling circles are respectively about 42 degrees in diameter and 33 degrees in diameter. If we now go to their linear size in megameters, it is found to be 507 megameters for the large phase circles and 400 megameters for the smaller vertex circles. And you see that these vertex circles, they correspond almost exactly with the early estimate of the giant cells' typical size by Bumba in 1969. Then the second scale level, n equals 2, yields 122 cells. It is important to note that this tiling level does not correspond to any observed solar cell scale. It is a little bit more complex. We have 50 circles plus 60 circles plus 12 circles, and this is 122 circles in total. Their size is, you see, for the first category, 244 megameters, the smaller ones 170 megameters, with a weighted average of 237 megameters in theory, according to this partitioning procedure. Then for n equals 3 is more interesting practically, because we have 482 cells, the size of which more or less corresponds to the scale of Macintosh's so-called intermediate sunspot group cell at the solar surface. The partitioning procedure is even more complex than the preceding one. We have only one primary circle which will be yielding an equilateral spherical triangle, and the other triangles obtained from this bisection of the edge yield otherwise only isosceles triangles, which are more and more distorted, this being a more acute isosceles triangle. So you see only the first one that can be, the first tiling circle that can be inscribed in the central triangle of a face is equilateral and is undistorted in terms of its proportions. The found weighted average diameter for all of these different categories of triangles is 117 megameter. It is, however, of foremost importance to recognize that if this procedure corresponds to an actual process in the Sun, process taking into account spherical symmetry and isotropy in the physical necessities of solar kinematic, then it is at the center of a face that will concentrate the regularities in the partition of the solar sphere in tiling circles. And as you remember from a previous video, we found that actually the large sunspot groups, the largest density at least in sunspots, is found to be at a latitude which is the latitude of the centers of the faces of the postulated icosahedron. At the next scale levels for n equals 4 and more, here we end at n equals 13, below which we cannot provide any postulate of observed solar cells. The formula is this, and is in fact absolutely straightforward, because it is only a multiplication by a constant factor 4 plus 2. So the first next level corresponds to no observed solar cell, but the next level yields 7,682 cells, and we shall see that it corresponds to a diameter and a surface which is that of supergranulation. So it is important to see that we do not have actually observed solar cell typical sizes at each level of the dissection of the solar surface. Maybe some of you who are seeing this presentation will think now that this approach is strange and is very complicated and not very convincing. But if you look at this table, you will see that our numbers of tiling circles correspond exactly to those of the one of the best known tessellation procedures for a geodesic sphere. It is called class 2 VK as a category of a tessellation procedure, cited, for instance, in this reference textbook. And you see this is exactly the same number of tiling circles. You see now in this table the entire set of parameters which define the tiling circles, their numbers and their dimensions, and the proposed correspondence with actually observed cells, giant cells, supergranulation, convective granulation, flux tubes, finally at the level n equals 13. You see that in the table there are voids, so we shall see why. The voids are at each even value of n, and the odd values correspond to actually observed or at least conjectured in the literature solar cells. Now, is there any systematic correspondence in position for the value of n for accepted cells, the major cells here boxed in the table, and the other cells which are only conjectured? We see that for n equals 3 plus a multiple of 4, we get only conjectured cell scales. The mega granulation, which is the sunspot group as proposed by McIntosh, the mesogranulation, and the smaller mini granules, turbulent mini granulation. The other levels among the odd values of n are the accepted major cells, which are boxed in this table. Giant cells, supergranulation, convective granulation, and we propose flux tubes at the bottom. If we compare now the dimensions of these cells as estimated here to what McIntosh in 1992 proposed, you see there is some discrepancy here for mega granulation in our jargon. For McIntosh, this is the sunspot group. But for the rest, we are very close to his estimates. In the 2017 update of his findings, we proposed 29.3 actually observed here, and here 7.4 actually observed, and here 1.75. This is now, ladies and gentlemen, the end of video 27 and of the discussion of the sizes of solar surface cells. In the next video, we will start investigating the last and important subject in the Fivefold Sun project, the spatial distribution of sunspots. I thank you for your attention.